A beam of light containing two different wavelengths, 400 nanometers and 700 nanometers, is incident on a diffraction grating which contains 10,000 lines per centimeter. Red and violet fringes are observed on a screen 1 meter away from the slits. The first thing we need to do is figure out what is the value of d, which is the distance between the lines on the diffraction grating. So the d is just simply equal to 1 over the n, where the n is the number of lines per meter, or in this case the number of lines per centimeter. So it's 1 over 10,000. 1 divided by 10,000 is equal to 1 times 10 to the negative 4. Since that was lines per centimeter, this is measured in centimeters. So we need to convert that into meters. 1 times 10 to the negative 4 centimeters is 1 times 10 to the negative 6 meters. The other thing we have to do is identify which wavelength corresponds to which color. So it says you have 500 nanometers and 700 nanometers, and you get red and violet fringes, and you have to know that the higher wavelengths correspond to the colors on the red end of the spectrum, and the lower wavelengths correspond to the colors on the violet end of the spectrum. So the red is 700 nanometers, and the violet is the 400 nanometers. So for part A, part 1 in part A, determine the angular position, which is basically just the theta, for the first and second order maxima for both colors. So now we're first looking at the first order violet. So when you rearrange the equation for theta, you divide both sides by d, and then take the inverse sign. So the inverse sign of m lambda over d is equal to, that's the inverse sign of the first order is 1, times the lambda for violet, which is 400 e negative 9, 400 times 10 to the negative 9, divided by the d, which we did up here, that's 1 e negative 6. And when you plug all that in, make sure your calculator is in degree mode, you get 23.6 degrees. For the second part of part A, the first order red, we're going to use the exact same equation. So this time we're going to be plugging in still m equals 1, but now we're looking at the wavelength for red light, which is 700 times 10 to the negative 9 divided by 1e negative 6, and that gives you an angle of 44.4 degrees. For part 3, we're looking at the second order violet. So it's the inverse sign, this time m is equal to 2, times 400 times 10 to the negative 9th, divided by 1 times 10 to the negative 6. That will give you an angle of 53.1 degrees. And for part 4, for second order red, inverse sign of 2 times 700 times 10 to the negative 9th, divided by 1 times 10 to the negative 6 is equal to, now if you try to plug this one in the calculator, it spits out that the answer is undefined. Well, what the hell does that mean? It means that there is no second order red. In other words, you're only going to see the central red spots, and then you're going to see the first order red on either side, so it's going to be one dot on either side of that, which is at 44 degrees, but you're not going to see a dot beyond that. So you're going to see a total of 3 dots, the one in the center, and then the first order on either side. Whereas with the violet, you're going to see a total of 5 dots. You're going to see the one in the center, you're going to see the 2 dots for the first order, which was at an angle of 23.6 degrees, and you're going to see the 2 dots at the second order, which is at 53.1 degrees, and you'll see that if you try to do a third order for violet, you would also get undefined for that one. For part B, Draw and label a graph of the light intensity versus position for the violet bands produced on the screen. So we know that for a diffraction grating, you have very sharply defined points. So the pattern looks kind of like this. You have the one very bright spot in the middle, and then a little bit further out, you have a lesser bright spot, and then further out still, you have a lesser bright spot, and then the same thing on the other side. So the pattern looks kind of like that. So the intensity this time is going to be a series of very sharp peaks. You have a really high peak right at the middle, and then there's a long dark patch, and then there's another peak which is not as high, and then a long dark patch again, and then another peak which is a little bit less high, and then the same thing on the other side. And these should be going all the way down to the axis. It's just kind of hard to draw that on here. And then the lesser peak right there. So that's what the overall sketch looks like. And on this one, I want you to change the graph axis to centimeters. It says millimeters on there, but that actually gets a little bit small. With this one, you could not use the approximation equation. That was the one that is the xm is approximately equal to m lambda L over d. The reason you can't do this is because if you look back at your answers in part A, you have all kind of rather large angles, 23.6 degrees, 44.4 degrees, 53.1 degrees. So because we're dealing with larger angles, we have to do it slightly different. So the pattern would look, or the sketch would look kind of like this. The angle, theta, which we've already calculated, and then we have the xm, and we know this distance here is L. To solve for the xm, you would have to use a tangent, because you see, if you know, with this angle right here, the opposite side and the adjacent side, we have the tangent of theta is equal to xm over L. So to solve for the xm, just multiply both sides by L, so xm is equal to L times the tangent of theta. And since L was given in the problem as 1.0 meters, you can just kind of ignore the L from this equation and just focus on the tangent of theta. So x1, the distance to the first bright spot, is going to be 1 times the tangent of the angle you got for first order violet, which was 23.6 degrees. That gives you about 0.437 meters, which is about 43.7 centimeters. So you could say this first bright spot here occurred at 43.7, and that's for both sides. Then you could do the x2, which is L tangent of theta. So again, 1 times the tangent of, and this time for the second order violet, which is in part 3 of A, that was 53.1 degrees, and that gives you an answer of about 1.332 meters, or about 133.2 centimeters. So you can label the next bright spot as 133.2.